So far, all of the functions and graphs that we've looked at have been defined the same way over the entire domain. For instance, if I said a function was f of x equals 2x plus 4, I don't specify for which values of x. That implies that my domain, this is for all x's from negative infinity to infinity. So if I were to graph this, using the process, the graphing a line using the slope and the y-intercept, the y-coordinate of the y-intercept is 4, and the slope is 2, which would be 2 over 1, so I would go up 2 units and over 1 unit and drop another point. And I would know, because it doesn't state otherwise, that this graph continues to the left and to the right forever. What we're going to look at in this section is something called a piecewise graph. For instance, let's say that I say f of x is equal to, and I say that it's equal to 2x plus 4 when x is less than or equal to 1. But it's defined differently. For instance, let's say it's defined as negative x when x is greater than 1. So what this tells me is that for the portion of the graph where x is greater than or equal to 1, that would be this portion of the graph, including negative 1 to positive infinity. I'm going to have a graph of y that looks like 2x plus 4. For the portion of the graph, oops, I did that backwards. For the portion of the graph that is greater than 1, which would be this, but notice I am not including 1. Strictly greater than 1 is this portion of the graph from here over, not including 1. This is the portion of the graph here from negative infinity all the way up to 1 and including 1. So that's what these two things mean. They mean you're breaking up the graph over the x-axis into two pieces. The piece where x is more than 1 and the piece where x is less than 1 or equal to 1. And then on this portion of the graph over here, it looks like y equals 2x plus 4. And on this portion of the graph over here, it looks like negative x. So I have to graph each of those separately on the piece where they are. So I could still graph using my y-intercept because the y-intercept is in this piece of the graph. Plot that point and then count up 2 and over 1. And this point right here, where x equals 1, is included. That's what this bracket means. That's what this equal sign means. So I do have that ordered pair. And then I would have the infinitely many points if I went down 1 and left 1, and down 2 and left 1, down 2 and left 1, and so on. This would go forever in this direction. But when I reach this line right here, something completely different happens. The graph now looks like y equals negative x. And I don't have my y-intercept here. It would actually be plus 0, but I can't plot that point because it's not in the piece of the domain that I need. So I could just create a little t-table here, and I could use numbers that are in my domain. In other words, numbers that are greater than 1. So say 2 and 3. And if I plug in to this function, y equals negative x, I would get negative 2 and negative 3. So I would have the point 2, negative 2. And I would have the point 3, negative 3. And 4, negative 4, and so on. So this graph would continue on in this direction. But I have a gap. Notice that I have a little gap here. This graph doesn't start at 2. This graph starts infinitely close to this line, this imaginary line. So I also have to say, well, what would happen if x were equal to 1? What would y be? But this point is not a point on my graph. But we do get infinitely close to that because of this strictly greater than. So this is going to be an open circle right here at 1, negative 1. And then I would have all of these points here. So to see what would happen to the graph where the open circle is, I have to go ahead and plug that number in, but keep in mind that's not actually part of the graph, and I show that using an open circle. And also be aware that this dashed line that I drew, this imaginary line, is not a piece of my graph. I just used that as a visual cue to see where the change would take place. I can also graph a piecewise graph with 3 separate pieces. For instance, let's say that when x is less than or equal to negative 2, my graph is x plus 3. And let's say that when x is between negative 2 and 3, including 3 but not including negative 2, x is 4. And when x is greater than 3 but not including 3, it is negative 2x plus 1. So when I draw my graph here, I'm going to have 3 completely different things happening. And my changes are going to occur when x is 3, right here, and when x is negative 2, right here. So in each portion of the graph, I will have a completely different looking graph. So this one here to the far left, when x is strictly less than negative 2, that's this piece over here, I'm going to have that y is equal to x plus 3. For this piece in the middle, from here to here, I'm going to have that y is equal to 4. And then for this piece over here, I'm going to have that y is equal to negative 2x plus 1. And each of these graphs cannot cross this line. And I can't have 2 dots on that line. So I have to have one an open circle, one a closed circle. So we'll look at that in a minute. First, we're going to figure out what the actual graphs look like. So if I can't use my y-intercept and my slope because the y-intercept is not part of this portion of the graph, I can just do a little t-table here. I can just find a couple of points. And so to find f of some numbers less than negative 2, I'm going to go ahead and use, and it's less than or equal to negative 2, so negative 2, say negative 3, negative 4. Those are some numbers in that portion. And I plug each one in. Negative 2 plus 3 is 1. Negative 3 plus 3 is 0. Negative 4 plus 3 is 1. So I can plot those 3 points. negative 2, 1. And notice that that point, because of the equal sign here, that point is part of the graph there. This is a closed circle. I also have negative 3, 0. And negative 4. I'm sorry, that should have been negative 4 plus 3 is negative 1. So negative 4, negative 1. And this portion of the graph looks like that. Now let's look at the middle piece here, y equals 4. As we learned in a previous video, that is a horizontal line. And I know that because it only has y equals and then some number. There's no x there. So that means that y is always 4, regardless of what x is. And that's what the graph will look like in the region between negative 2 and positive 3, not including negative 2 and including 3, because there's no little equal sign here and there is an equal sign here. So I'm going to have the line 1, 2, 3, 4, the horizontal line, y equals 4, and I'm going to have an open circle here for where x is negative 2, and a closed circle here for where x equals 3. And again, that's because we do not have an equal sign here, and we do have an equal sign here. And then I can do the same thing in the far right region. Do a little t-table, and what I'm plugging into here is y equals negative 2x plus 1. So I want to see what happens at 3 and then numbers bigger than 3. But I have to keep in mind that this point right here at x equals 3, because I do not have an equal sign, is going to be an open circle. So I can plug those numbers in to this value, y equals negative 2 times 3 is negative 6 plus 1 is negative 5. Negative 2 times 4 is negative 8 plus 1 is negative 7. And then negative 2 times 5 is negative 10 plus 1, which is negative 9. And so I can plot those 3 ordered pairs. And notice the 3, negative 5 right here is an open circle, because when x equals 3, y is 4. That point already exists up there. And then 4, negative 7 right here. And yes, and then 5, negative 9. And I have my portion of the graph over here. That looks like this. So that's what the piecewise graph looks like.